You guys see my screen now, correct?
Yes, sir.
Yeah. And I can't stress enough that if you have a question, please let me know, because it's no longer about physics. Now it's about the final. So if you don't care about getting the physics right, okay, fine, but you should care about the final. So today's lecture is actually about designing flight control system. Sometimes we call it autopilot, right? Design. Standard or technical name term for it is actually Stability Augmentation System, SAS, or Control Augmentation System, SAS and CAS. All right, and let's try to review what are the basic steps. I mean, if I want to design a control system for anything, submarine, for example, it doesn't have to be an airplane. What are the basic steps? First, you need to know your system, right? A mathematical representation for your system. Please give me a transfer function or a state space model, right? So that I can apply my control theoretic tools to it to design a controller. So please write your system in a good form. So for us, and if you take 170, so this is transfer function. Here we have been dealing with state space models. And in particular, if we apply for the entire airplane, we really have been doing that. We started by the 9x9 nonlinear differential equations of motion. And we linearized to get 4x4 longitudinal. We even did further decoupling. How many modes in the longitudinal, folks? You'll be asked about this next week. How many modes about in the longitudinal?
2, short and long.
Very good. Short period mode, long period mode, right? Okay, and the other motion is the lateral. Sometimes we say it's 5x5, or actually when we ignore the ignorable coordinate, I mean, we're left with another 4x4 lateral. If you don't like the 4x4, you want to include 5, it's fine. And how many modes in the lateral? Anyone else other than Jeremy?
3.
3, very good. Thank you. Thank you, guys. This is the type of questions that you'll find in the final. So Dutch roll mode, right? The very serious mode, oscillatory mode. Airplane is skating, is acting as a tree leaf. And you can imagine that it's really annoying to passengers and pilots. One of the most concerning modes in the airplane flight mechanics. And then we have the rolling mode, which is the nicest mode ever, right? The fastest and nicest, thanks to the wing damping. And in the next lecture about the advanced topics, which will not be in the final, we will talk about wing damping and this rolling mode in other unconventional scenarios. And then, oopsies, and then the spiral, right? This is oscillatory mode, 2 states, the short period, W and Q, right? Oscillatory mode, long period, U and theta. Oscillatory mode, Dutch roll, beta and R, or V and R. The other 2 modes are not oscillatory. So this is the rolling mode P, the spiral mode about the R dynamics, but it's not the yaw dynamics. The yaw dynamics is here in the Dutch roll mode. This is coupled roll and yaw. If you remember this very long discussion about the spiral mode, that the airplane, if it's unstable, the airplane will keep spiraling, will keep rolling and yawing, and of course losing altitude. So luckily our airplane flight mechanics is decoupled now into 5 small systems. Each system is a small system. It's just 2x2 for these 3 modes, and actually 1x1 for the last 2 modes. Any question about that? So when we want to design a flight control system and a flight controller, So the very first step is to write down the equations for your system. We will no longer go to the 9x9 nonlinear equations of motion. We will focus on our objective. If you want to adjust the short period modes, the short period mode, here is your system, 2x2. If your concern is the Dutch roll, here is your system, the V&R, okay? So for each one of these 5 modes, we really derived the A matrix. Remember the system? When I say system for us, it's state space model. It's x dot equals ax plus b times the input, which we give the name u tilde, right? So in a different color. And please, whether you studied or not, this thing will be next week in the final. Will have a large points on this lecture. So stop me if you have any question. So any system, like it's defined by a numerator and denominator of transfer function in 170, in the language of state space model, it's defined by its A and B matrices, right? So for each one of these, we really derived A and B matrices. So we have an A matrix for the short period, we have A matrix for the long period, we have A for the Dutch roll, we have A for the rolling mode, I'm sorry. And the rolling mode, the A for the rolling mode is just a number, right? Because it's just a scalar, it's one state mode, the same for the spiral. So A here is the same as lambda, A here is the same as lambda, right? All right, so I'm done with my system. So this is what we had really in lectures. Maybe this was lecture 14, if you want to review, and this was lecture 15. So this is why I'm saying this particular lecture has stuff from almost everywhere. All right, so this is the first step. Write down the equations for your system. We're done, and we're gonna recall that today when we do examples. We're gonna do 2 examples. The second step, what's the second step? Let's see. I have my system. I want to know what do we want to achieve? What is the desired characteristics? Desired response. You want to design a controller to achieve what? Any suggestions for what is? Go ahead.
Level 1 flying qualities.
Very good, very good. So the desired response. What's the desired response for anything, for a submarine? Well, this is a very hard question, and actually, it is answered through experience. An experienced control designer for this system who designed several controllers before, he learned or she learned that this controller works, that controller doesn't work, and so on. So they build experience. So this is invaluable experience. For airplanes, this question is very important as well, like any other system, but because the airplane is a very important system, we don't leave it for experience. It's tens of years, pilots flying and giving opinions, and these are tabulated in lecture 16, right? So this is the flying. For us here, this is really the flying qualities. So the desired response of the airplane is simply what we call the flying qualities or the handling qualities. This was lecture 16, just last lecture. And for just giving you one example of these tables, this is, for example, the table for the short period mode. This is just one example. And as you guys recall from that lecture, we have that the airplane now are classified in classes: small airplanes, medium weight, heavy, and the fighters interceptors, 4 classes, and the flight phase categories, 3 categories. Category A, where we're not doing any takeoff and landing, but we're doing something that needs really precision and maneuverability. Air-to-air combat, weapon delivery, and so on. So this is Cat A, something military. Cat B, it's also not takeoff and landing, so it's what we call non-terminal, but now we're doing something that doesn't need any maneuverability. It's just cruise, climb, and so and so. Cat C is something near the airport, near the terminal. So this is a takeoff and landing kind of thing, okay? These are the three flight phase categories. And now we have these tables, a table for each of these 5 systems, okay? So given a system, given its desired response, what is the desired response? These are the level of flying qualities, the pilot's grading for the airplane. So 1 is the best, 2 is okay, but you know, it's an increased pilot workload. 3 is inadequate to perform the mission. So of course, if we want to design, I'm going to design for the best. I'm going to design for level 1 flying qualities, okay? So I'm going to use these tables to tell me what is the for level 1 fly qualities, what is the damping ratio that is required, for example, okay? All right, I mean, we're going to do this in an example. Any question about this logical step? First, write down your equation. Second, what is the desired response? What do you want to achieve?
Really quick, Professor. So
Yep.
for like the level 3, since there's no max, like no upper bounds, like on the test, is it just if it doesn't fit in 1 or 2, it defaults to 3? Is that how that works?
Of course, yeah.
Okay.
Unless it's below 0.15, then this is, and I don't think that this will happen. This means that, you know, there was no airplane among the hundreds that they flew was below 0.15, okay? So this is very not typical. So number 3, okay, you have your system, you know what you want to achieve, okay? You need to decide about the control technique. Control technique, technically we call it control law. What is the method for your control? Like, are you going to use PID controller, for example? Is it P, PI, PD, PID, lead, lag? You know, are you going to use robust control, H infinity, optimal control? What are you going to use? So for just this class, I mean, it's not a control class. And you know, frankly speaking, the entire control theory is about this third step. All right, so here we do state feedback, right? Simply, which is quite powerful if you can do it. State feedback. So we do pole placement, which is our control law. So the law that governs the input that you're gonna provide every time step is that your input is given by negative k as a matrix times x as a column. So it's negative k1 x1, negative k2 x2, and so and so. Okay. So please go and measure every state, every x, and we're gonna tell you a way to design these gains k's offline, and just substitute this equation every single time step to get the right amount of input. And this is what we did in lecture 12. Right, so this is why I'm saying this lecture really brings stuff from lecture 14, 15, 16, and 12 together. So this is why it will be in the final in 2 problems. All right, given my system, given the desired response, and given a way that allows you to achieve this response. So this lecture in particular, actually, this lecture 17, which is the last lecture, is simply, like I always say, just do it. Is just do it together. Okay. Any question? Any question? So when I substitute this negative kx for u tilde here, so please replace u tilde by negative kx. So I have a term that is ax from here and negative bkx from there. So I'm gonna collect all these, and I will have x dot equals a minus bk multiplying by x. And when you look at this, x dot equals something times x. This must be my new A matrix, which we call A closed loop. So after substituting by the feedback, okay, so we closed the loop already. My A matrix changes from just A, the old one, to A minus BK. And now it's my role to my task to adjust these Ks such that the overall or the new A, the A closed loop, behaves like I want here. Let's have examples. So the example that we started last time, so this is an example. We have a fighter aircraft. Now I will not just let this word pass like before. Fighter means something. Fighter means what? I go to the classes and these will be provided in the final. Okay. These tables, everything for the flying qualities will be provided in the final. So you can see here that the fighter airplane is just class 4. Okay. So this is an important piece of information. A fighter aircraft has the following characteristics during landing. Okay. During landing. Again, I cannot let this pass because now landing means what for the flight phase? Because it's not only the class, it's not only the type of the airplane, and also what it's doing. So it's a fighter airplane, so it's class 4, fine. Landing, you go to the flight phase category, you will find that here landing actually belongs to Cat C. So now I know it's class 4 and Cat C, fine, okay. What are the characteristics? Well, it has, I mean, we had this example already, this negative 90.52 feet per second squared. M alpha is negative 2.06 radians per second squared, and MEQ was negative 0.6 per second. All right, so these are the characteristics, and we need the level of flying qualities. This is what we did last time. Well, we simply went to the expression for, this is the short period mode, and the short period mode doesn't care about omega n, it actually just cares about zeta. So please give me zeta. We have expressions already for omega n short period and zeta short period, so go and substitute directly. So please include these expressions into your cheat sheet. Zeta and omega n for all these modes, right? And the lambdas for the last modes. So omega n short period was actually negative M alpha and ZWMQ. So we're gonna do direct substitution. We got omega n last time, 1.53 radians per second. I don't care about it, but I needed to determine zeta. Zeta is negative ZW and MQ divided by 2 omega n short period. Just direct substitution gave us zeta to be 0.34, if you remember this. So I use this table, I can use this table in two manners, one for analysis and one for design. For analysis, I'm analyzing an already given airplane to determine the level of flying qualities. Would it fly good or bad? I have airplane characteristics. I don't need to fly it again to know if it will fly good or bad. I don't need to waste my time, money, and energy and everything. We already have data from before. We have legacy we can exploit. Okay, so simply by doing this calculation, I got here 0.34. This is not clear. 0.34 for zeta of the short period. I go to the table to determine, will this fly good or bad? Simply 0.34 doesn't belong to level 1. Does it belong to level 2? Yes, it belongs to level 2. So this is what we determined last time together. This was level 2. So it will not be the best airplane to fly. It will be flown, but okay, but with an increased pilot workload. Okay, fine. And then I left you a quiz, which is the same airplane at a different flight condition. So now at a different flight condition at was 25,000 feet altitude, U-naught 800 feet per second. Here actually U-naught was, so during landing, U naught was 200 feet per second. This is what we did last time, nothing new so far. Okay, I'm just reviewing because we're gonna need this information again. At this new flight condition, we have new data. So now the Z alpha becomes 649.25 feet per second squared. M alpha is negative 14.78 per second squared, and MQ is negative 1.08. Did I do this? Yeah, that's right. All right. So I have new data, fine. I'm gonna go and use the exact same two equations with new numbers, and you guys did that already for the quiz. So we got omega n short period now is something different. This was 3.96, so it's a for you to determine if you solved this correctly or not. And zeta short period is just 0.24. So it's interesting here. Why? Because look at this. What is MEQ? Again, the final is next week. What is MEQ? Anybody can tell what's MEQ?
Pitch damping.
Very good. This is pitch damping. And you look here, it's 0.6. Now it's 1 point something. So it's almost double kind of thing. So you think that the pitch damping enhanced, right? It almost doubled. So you think that if I'm level 2 here at the sea level during landing, I will be better there. But actually, no, it's the other way around. So, so what happened here is that instead, although the pitch damping coefficient, MEQ, increased significantly, the damping ratio itself, which is, you know, the relevant factor for the short period mode, actually decreased. So I don't know if what you did, guys, in the quiz, but if you got zeta around 0.24, your solution is correct. And let's go together and get the level of flying qualities. What level of flying qualities is that? Again, I mean, which column? What column we're talking about? Well, it's the fighter airplane, so class 4, short period mode doesn't care about classes. It cares about categories only. And now we're talking about here, the category was air combat, because at this altitude I could be doing many things, right? Here it was air-to-air combat. So air-to-air combat, if we go to the categorization, this is military. So this is Cat A. So you're gonna go to the table by Cat A, and I have my damping ratio 0.24. So what level of flying qualities is that?
Level 3.
Level 3, very good. So I was level 2 during landing, and when I went to another flight condition in another mission, air-to-air combat, it actually became level 3. So it's completely inadequate to perform the mission. All right, if both of them were level 1, I would have been okay, and I would not need really to design a flight controls. If your airplane is already good, please don't go and design a flight control system. Okay, we do it only if our airplane has a bad behavior, like this one, level 3 flying qualities. This is inadequate to perform the mission. So I'm gonna take the worst case scenario among the two, which is simply this red flight condition, because it's level 3, it's worse, right, than level 2. And I'm gonna design a flight controller here to bring this this flight condition into level 1. And if this is level 1, obviously this will be enhanced accordingly and become also level 1. Okay, any question about that?
Professor, is there
Yep.
a reason why, like, aside from like just what we've been given, like, why are we looking at the short period mode in particular?
In reality, you're gonna look at all modes. This is a particular problem. It's about a single mode. Okay. When you do it for an airplane, you're gonna do it for all modes. So for the worst, and we're gonna do another example after this one for the Dutch roll. And these are the most two important modes, frankly speaking. And I'm like giving you a hint here that in the final, yes, it will be about short period and Dutch roll, exactly the same as your homework also was about short period and Dutch roll, because these are the most two important modes for the airplane. And also the other modes are, quite simple. It's just one state. So for the worst case, which is this one, let's design stability augmentation system that achieves level 1 flying qualities. Okay. Question, please. Questions.
Hi, Professor. I have a question. You said before that basically once we move level 3 to level 1, that'll also improve level 2. Is it possible to, I don't know, can you bump up one of them too high such that it goes above 1.3?
No, we will not. So we will not do that. Let's see. Let's see. So how can I design a controller? Here are the steps. First, write down your system. So let's write down our system, please, for the short period mode. And again, this is something that you need to include in your cheat sheet. Include the system structure for all the 5 modes. So the short period mode is W and Q. So this is, I'm not gonna do it again. I'm not gonna derive it again. I'm not gonna do anything. Just copying out of the cheat sheet. So this is ZW U naught MW MQ. This is lecture 14 times W and Q plus here in the B matrix for the short period mode. I mean, we derive the A matrix together. For the short period mode, simply, we have 2 controllers in the longitudinal. Anyone can say what are the controllers for the longitudinal? I mean, in general, we have 4 controllers, right? And the 4 controllers are divided into 2 here and 2 there. What are the 2 in the longitudinal?
Thrust and elevator?
Exactly, thrust and elevator. And if we want to control the short period mode, which one do you guys like to use, thrust or elevator?
Elevator.
Elevator. So short period mode is all about pitching dynamics. So of course, I'm going to use the elevator, right? So this is the Z delta elevator and M delta elevator here. So this is standard short period mode. And I'm given everything here. I'm given Z alpha, I'm given MQ, I'm given U naught, but I'm not given ZW and MW. I'm given the alpha version of it. And you guys should be expert in this. If W is U naught times alpha, then ZW is Z alpha divided by U naught, and the same for MW, right? ZW is Z divided by W. So I can really now just write down my system. W dot Q dot equals U naught was 800, MQ was negative 1 point something or 0.08, and the other 2 numbers is just please get your ZW and divided by get your Z alpha here and divided by U naught, which is 800. So this will give you here negative 0.812 and here negative 0.0185. Any question about that? ZW and M, I'm sorry, Z elevator and M elevator, these are given actually negative 0.254, negative 0.199. So these are given. I can include them here as well if you like. Z elevator is negative 0.254, M elevator is negative 0.199. So this is my system. The first step is done. Any question about the first step? Any question about the first step? Straightforward, huh? Just get it from this cheat sheet and substitute by the numbers. All right, what was the second step to design your controller? Please give me the desired response. What is your desired response, folks? We're designing for this case. Omega n was 3.96, zeta was 0.24, so it was not adequate. And we were cat A here, military. So like I told you, I can use this table for two different purposes: for analysis, analyzing an existing airplane, like what we have done in the last two examples in the level 2 and level 3, and to design. When I design, of course, I'm designing always for level 1. I will never design for level 2 or 3. So here I'm designing. So this is the design step. So this is the range. And like I said, we are in Cat A because it's military stuff, air-to-air combat. So I'm in here. So I have the minimum and maximum. What do? We always shoot for the middle of the range for robustness. So here we're gonna shoot for the middle of the range, the average between 0.35 and 1.3. So this is second step, the desired response. The desired characteristics, what is that? We have Cat A. We go and do the zeta average for level 1, of course, level 1. This is 0.825. And what about omega n? Because we always need zeta and omega n. What about omega n? I mean, we don't care, the pilots don't care. They never complain about the omega n. So it's better to keep it as is. So keep omega n at, it was what? 3.96, I guess? Yeah. This immediately, these two pieces of information gives you what? The characteristic equation, s squared plus 2 zeta omega n, s plus omega n squared. So my desired characteristic equation is s squared plus, multiply please, 2 times zeta times omega n. This is 6.53 s plus omega n squared. This is 15.68. This is the desired characteristic equation. Any question about that? Please, if you have a question, stop me. Folks, this is your last chance. Next lecture will not be in the final. We will doing something irrelevant, okay?
Hey, Professor.
Yep.
Just a quick question. Where is this omega n again from? I kind of lost track of where it came from.
No, that's fine. I mean, we were at the beginning, we were analyzing an existing airplane with existing characteristics. So in order to compute zeta for the short period mode, actually we need omega n. And omega n we compute it from this equation. So we compute it to be 3.96 from this data. Okay.
Got it. Thank you.
Mhm.
And could you clarify a little bit more about the Z alpha and ZW? For some reason, I'm not seeing the connection there. Oh, right there. Okay, perfect. Yeah.
I'm sorry, what's the question again?
So you just take your given, which is Z alpha, and
Yeah,
you
divided by
non-dimensionalize by U naught, and that gives you Z.
Yeah, divided by U naught.
Okay.
Yeah, this is a standard relation. Yes, exactly.
Yeah.
All right, so I'm done with step 2, which is, so here is my system. Here is the desired response. Then what is your control technique? State feedback. So let's get our A closed loop and try to design the gains such that we have this response. So let's do that. So the third step, which is the red step, state feedback. Gives you the A closed loop is simply A minus BK, right? So let's do it together. So A closed loop is equal to, let's copy the A matrix together. So here is the A matrix. All right. And let's copy the B matrix together. Okay. So this is A minus B times K. Folks, this is, I don't know why people really do it. I've been teaching this for 6 years, right? This is actually the 7th. And I taught it many, many times also, like several years before that in different places, not flight mechanics, but control. And I don't know why people keep doing this little step wrong. Because probably the first time they do it in the final, and it's too trivial to make them confused. K is a row matrix. So this is K1, K2, simply. Okay. And this multiplication is, this is the thing that I'm saying, it's so trivial that it's confusing. Because when we multiply matrices, we multiply rows by columns, but here each row and each column is just a scalar, so it makes people confused. This is a row, this is a column, this is a row, this is a column. So let's do this multiplication together. So negative 0.254 times K1, I'm done. Negative 0.254 times K2, negative 0.199 K1, negative 0.199 K2. I hope this is clear enough. And now simply we're gonna subtract this matrix, the previous A minus the BK that we just got, okay? Just term by term, subtract these two matrices together. So we got a closed loop to be, this is point plus 0.254 K1. Maybe I can use another color as a separator. 185, this is a little bit boring, but you have to do it for the final to get a job and graduate. This is 800 plus 0.254 K2. And actually industry is much more boring than even solving this problem. So that's fine, it's a little training. So this is my A closed loop. Questions about that? Fine, how can I adjust this to meet this desired response? So what's this? This is the desired characteristic equation, characteristic polynomial. So simply get the characteristic equation from here and compare. Done. How can I get the characteristic equation from this A matrix? Any idea?
You take the identity matrix times lambda and then subtract ACL from it.
Exactly, lambda I minus A, right? So let's do that. I'm gonna copy my A here. Oopsies. Okay. Did I do something bad? Anyway, Control C. I'll keep this again, and I'll copy one and put it here. Okay, fine. So this is lambda I minus A, and I need actually the determinant. Let's get the determinant first. Okay. So this is A, I just copied A. So let's put minus sign in front of everything for A. So minus, so this becomes plus. This becomes, oopsies. This becomes minus. This becomes minus. This becomes plus. I mean, whatever, I don't know. So plus. I'm doing minus everything I had from before, okay? Plus and minus, all right. And then I'm gonna add lambdas over the diagonal. So lambda here and lambda there. And here is my separator from before. Any question about that? And a tedious work is to multiply these together minus the other way around. So this is lambda squared plus 1.8, actually 92 minus 0.254 K1 minus 99 K2. This is all multiplying lambda plus some free term, which is 812 K1 times this guy as a whole, 1.08 minus 0.199 K2. This is all minus the off diagonal. This thing was minus, I'm gonna have here as a plus, the 800 and 254K2 times minus 0.199 K1. We're done. And you need to, flesh this out. One sanity check for yourself to make sure that you didn't do something wrong in the final is that you're gonna see always this term of K1 multiplying K2. it must always cancel with the K1, K2 coming from the other way around. This is a linear system. We start with a linear system, x dot equals ax plus bu. No nonlinear terms at all. The control law here, u equals minus kx, is also linear. So no nonlinear terms are expected at all. If you see k1 square, k2 square, k1, k2, you did something wrong. Okay. So this is a sanity check for yourself. So let's flesh this out. I'm gonna take this as is, copy it here, and let's flesh the free term together and just copy it. This is plus what? This is 1568.15947 K1 and 0.157 K2. This is my characteristic equation of the closed loop system, and this is the desired one. Let's get it. And simply compare coefficients. So the coefficient of S or lambda is the same. This is one equation in K1 and K2. The coefficient or the free term is the same. So another equation in K1 and K2. Solve these two linear equations. Simple to get K1 and K2. K1 here is 0.023 and K2 is around actually 1,000 times of that. Let's see why. Any question? Any questions so far? Fine, we got the gains. Like every control designer is obsessed with the gains. We worship the gains. And then what do we do with them? So, and this is something that you're going to do in the final too and in the homework, because it's just, it's not just cold problems that we solve and we don't know what are these numbers. I mean, points will be taken off from you if you just get the gains and go back and go home. First of all, we need to know what is the control law. What's your control law? My input is negative k's times the x's. My input here was what? What was the control input in this system? What was the control input?
Delta elevator.
Very good. So my delta elevator is negative k1 x1, negative k2 x2, right? So let's substitute. So my delta elevator at any time instant is given by negative k1 times my first state. In this particular formulation, my first state I started with was w, and my second state was q. In other problems, like the homework problem, for example, you're given the short period in terms of alpha, not in terms of w. So it depends on really what state you started with, okay? So here it was w minus, so minus is plus. This is times q, the second state. This is my control law. What do you mean control law? I mean, the main objective for control design is to determine how much input to apply at each time step, how much input your elevator servo will give at each time step, okay? And it simply says, please go and measure your W, measure your Q, substitute in this equation at each time to give you the right amount of elevator deflection at each time, okay? That will give you this response, that will give you this damping. And this damping will make the pilot happy, because when the pilot sees this damping, he or she grades this airplane as level 1 flying qualities. Okay, any question about that? Fine, so the control designer job ends here, then starts the job of the implementation engineer or system engineer. How can we implement this on an airplane actually? So let's see. Here is your airplane. Okay. And our input is the elevator. Here is the horizontal tail. Here is the elevator deflection, right? This is my delta elevator, and I need to know how much elevator should I give at each time. This is your pilot who is giving a command, doing some maneuver. Now, in addition to the pilot command, you're doing something for feedback control. But this feedback control requires what? Requires measuring states, measuring W. What is W? W is just simply a constant times alpha. So let's measure alpha together. So here is your wing. We're gonna put some alpha vanes on the wing to get me the angle of attack alpha. And now from the angle of attack alpha, you multiply by what to get W? Alpha multiplies what to get W?
U0.
U0. So please put another sensor, put a tube or something to measure the airspeed. Finally, you have W. And I need the other state. So I got W. I need the other state Q. Put another sensor. We call it gyro. And gyro is not much nicer than the angle of attack sensor. Guys, remember the angle of attack sensor is the main reason behind the 737 stuff that happened last year, right? It was all because the angle of attack sensor was giving a wrong reading, right? Was giving a very high angle of attack, whereas the actual angle of attack was just normal. All right, so I have the two states. I have W and Q. Your control design says that please multiply these by static gains. So I have these numbers, K1 and K2. From this design operation offline on paper, I have these numbers. Now I'm going to use them here. The result is go and add all these signals together. This is negative feedback. In addition to the pilot command, right? And the result is what is going to the elevator servo. Here is a servo motor for the elevator that moves the elevator. Any question about this implementation? Any question about this implementation?
I have just one in general. So if we have like a negative gain value, does that mean that it's telling the system like if it senses the angle of attack to be like positive, then it'll just treat it like it's being taken negative, like it inverts it basically?
Not necessarily. Like I mean, you have to indulge into the system sign conventions to know what is going on. But yeah, I mean, you're going in the right direction. Typically, the negative feedback is the standard, is the convention. And if you found your gain, but again, this is not a general rule, right? It's maybe in most of the cases, or if everything else is conventional, if you found your gain is negative, which means that you're going to do positive feedback, it means that your system maybe was giving more than enough, more than sufficient, and you're taking away out of its own feedback characteristics. So let's do that here. Let's do that here. Actually, when I ask you in the final, you got the gains, then you need to write down the control law. You don't need to do the implementation. This is for yourself. But you need to tell me what do these gains represent physically? What do they mean? What do they do to the airplane characteristics that we spent time and time with it? Stiffness and damping for the modes. Okay? So let's do that together now. How can I do that? Well, please get this control law. This is very important. You have to do it in any problem in the homework and the final. So this is the physical explanation, physics. Okay, so I have the elevator deflection like this, fine. And as you guys know, W is really U0 times alpha. So I'm gonna replace this by U0 times alpha, fine. When you apply elevator for the airplane, what happens? Anybody can tell? When you apply an elevator deflection, what happens? What you actually give? What does elevator do for an airplane?
It's going to create a moment about the.
Exactly. So there is a change in the pitching moment, which is simply m delta elevator times your delta elevator. And I have m delta elevator here. My m delta elevator was negative 0.199. Very good. So now I'm going to substitute my delta elevator here. So my delta m, the change in the pitching moment characteristics of the airplane is, so it's m delta elevator times, let's substitute by your delta elevator, it was negative whatever, k1 times u naught times alpha, right? Negative k2 times q. So this is m delta elevator k1 times u naught times alpha plus m delta elevator in negative times k2 times q. Look at this and tell me, please. Change in pitching moment is something times alpha. What must be this thing? If your moment is change in the moment is something times the changes in alpha, what this represent? This thing.
M alpha.
This is exactly m alpha by definition, and this is exactly what?
MQ.
MQ, very good. Let's compute this. Let's just multiply the m delta elevator by K2 to get the change in MQ and the change in m alpha. So the change in MQ was about negative 4.64 per second. And this is versus the original value was how much? It was like negative 1.08. This is the additional MQ. What's the MQ for my airplane? MQ is the pitch damping. So originally I had this pitch damping. Now I created virtually pitch damping through feedback by this amount. So the total will be the two added together. So I provided 4 times more pitch damping for this airplane. How could I achieve that? By changing the horizontal tail area. I could have achieved that by multiplying my horizontal tail area by 5. Which of course, if you are proposing to your chief engineer, they will fire you, right? Right away. So here we're doing it virtually because the airplane naturally does this. The airplane senses Q, pitch rate, and applies a pitching moment opposing to Q by this amount. For every Q radians per second, it applies 1.08 pitching moment. So I do the same. I sense Q by placing an actual sensor to measure Q, which is the gyro, and apply a delta elevator, which will apply a moment that is proportional to Q by this amount. And adjusting this, adding this extra damping, like 5 times damping, really brings the damping ratio from the 0.24, which was not accepted at all, to the 0.8, the value that I designed, which is in the middle of the range, which will satisfy pilots. Any question about that? Any questions? The same happens for M alpha. And you should do the same. We should get actually the change in M alpha and compare it to what before and see how much additional pitch stiffness we provide. But in this case, if you see here, it was a clever choice to maintain the same omega n from the beginning. So I know that I had to modify zeta. Zeta's too bad. And I found pilots didn't care about omega n, so I maintained it the same. And why this is clever? Because omega n represents what, folks? This is the short period mode. Omega n is what? In general, not the short period mode. Omega n is what for any system? What is omega n?
It's the natural frequency at which it would oscillate at.
Very good. So this is its meaning. So it's dictated by what in the system, in any system?
Spring.
Spring, very good. Omega n is your spring, right? The natural frequency is dictated by the spring, square root k over m, right? So if I kept my omega n, it means that I am keeping my spring constant, my stiffness. I'm not changing it much. So indeed, the K1, which will change the stiffness, will be quite small. Look at the ratio here is actually 1,000 times the one for the damping, almost 1,000 times the one for the stiffness. And if you're not changing the stiffness, if I'm not changing the M alpha, it's as if I can really get away with this sensor. I don't need this term. This term is quite small. The additional M alpha is not that big, and I can just simply ignore it. So it's as if K1 is 0. K1 is quite small, so it's as if K1 is 0, which means that you don't need this alpha measurement, which is very good because now you saved sensor, right? Which comes with its own hassle, filtering, signal conditioning, and blah, blah, particularly if this sensor has a bad reputation. Angle attack sensors are not that good. And like I said, they are really the main reason behind the 737 crashes in the last year. So that's it for here. Any question about that?
Professor, I do have one question up on the sort of the diagram of how the whole system would work. Does this mean that it only works if you have a purely fly-by-wire system? Like, what would happen if you had cables, like in a small aircraft, connected to the controls? Is it possible to still do feedback?
Yeah, we can do it by so fly-by-wire has to do with we can do feedback, of course, without fly-by-wire. Fly-by-wire has to do with the pilot command. In an airplane that flies without fly-by-wire, so there is no fly-by-wire, just direct cable. Okay, this goes directly to the elevator. All right.
Yeah.
But for an airplane that flies by wire, this means that this will go to the computer, and the computer will interpret what the pilot needs and does it on its own. So we can still have feedback superimposed to the pilot command going directly to the elevator servo. The only difference, is just this command will not, if it's fly-by-wire, it will not go directly to the servo. It will just go to the computer first. It's just an additional layer to this. Okay.
Okay, interesting. Thank you.
Yeah, and there is an interesting story. You know, the F-16 is the first fly-by-wire airplane fighter, and its pilots at the beginning, they were saying something like, "You never fly F-16; it flies you," because whenever they they pull the stick or they're doing something, they feel like the airplane is not responding as they think. I mean, the airplane is doing its own thing. All right, let's have another example on the lateral, and we're done with the course.
Professor, I have another question.
Yep.
So more often than not, do we want to try to cancel out that alpha?
I'm sorry, say it again. I did not say it again.
So more often than not, do we want to have that alpha cancel out?
Yeah, and this is a general rule of thumb. If you can attain the same response with fewer gains, which means fewer sensors, this is a very commendable thing. Particularly if there are some sensors that really worse than others. Like I said, gyro, we play with gyros all the time, and they are really nice sensors. Angle of attack, not the same. So another example on the lateral though.
Thank you, Professor.
Now, yes, Manuel. Oh yeah, you're welcome, Manuel. Now a trainer airplane. You guys know now that we don't let these words pass now, right? Because they mean things that we will really use. So a trainer airplane, we go here, aircraft classes. So the first thing, trainer. So this is really class 1. Good. And this is during landing. And landing is cat what? Anyone remembers? Let's go to the table.
Cat steer it.
Yes, it's cat C, very good. So you can see here, This is landing, it's Cat C. So we know now it's class 1 Cat C. And it has the following lateral characteristics. Let's read it off. Again, the lecture notes are a bit detailed, so you can rely on. And here is the characteristics. So this is lateral flight dynamics, and it's up to you. It's your task to extract the Dutch roll out of it, or the roll, or the spire, whatever. But mainly we'll be concerned with the Dutch roll, okay? So we'll see how to do it. And what's required? It's required to design stability augmentation system to achieve a level 1 Dutch roll flying qualities and use values that are 25% higher than the minimum. We'll come back to it. So actually, let's remove it and come back to it, because you guys know, maybe actually it's not a bad idea. Fine. 3 steps. Let's do it. So first step is what? What's the first step? What should I do? How can I start?
Define your system.
System, my system, very good. The system here, they are talking about the Dutch roll, right? So let's get the Dutch roll, please. Anybody remembers what are the states of the Dutch roll mode? What are the states? This is something you get from your cheat sheet, but anyone with a sharp memory here?
Side slip.
Side slip, very good. Yes. Remember always the skating. Dutch roll is skating. So this is side slip. Side slip is either V or beta. Here is given in terms of beta, so I'm going to use beta. And what else?
R.
R, very good. Beta and R. So this is beta dot R dot should equal something times beta and R, right? The standard state space model plus some input. Very good. Let's fill these matrices. If we have numbers, I'm going to substitute by, n beta, nr, blah, blah, blah. But if I don't have numbers and I'm given the system already, you need to extract it yourself. And this is really, the Dutch roll mode was easy in extraction because it was just by the indices of the states. The indices were 1 and 3, right? Beta and R are the first and third states. So it's the first and third column, first and third row, and we're done. So this is negative 0.05, negative 0.98, 0.3, negative 0.15. Any question on filling out this, my A matrix for the Dutch roll here from the full system? Any question, folks? Go ahead.
So in lecture 15, we said it's V and R. How did you get B dot or beta as the first state?
Yep. Let's see. Let's just and this is very similar to the W alpha relation. There is the exact same thing between beta and V. So okay, I can really write it down in terms of V or beta. The same thing here. I can really write it down in terms of W or alpha. Okay. And indeed, the question, do I have the question here? Indeed, the question here, homework 8, where's homework 8? Yes. The question in homework 8 is actually given for the short period mode in terms of alpha and Q. Okay, so you should be ready with either representation. And the relation is simple. Sometimes it becomes confusing, but just write this in front of you. V is equal to U0 times beta and W equals U0 times alpha. Any questions about that? Let's determine the input here. I have 2 inputs, aileron and rudder. And we need to pick one. Which one do you like to choose for controlling the Dutch roll mode?
The rudder.
Very good. You're going to choose the rudder because it's mainly about yaw dynamics, right? The Dutch roll mode. So I'm going to use the rudder here, which means the second column here, because this is the one that is multiplying the rudder. And again, I'm selecting the first and third. So this is 0 and negative 0.6. Let me have my rudder in red. Any question? So this is my system, x dot equals ax plus bu. I'm done with the first step. Any question? What is the next step? What should I do now? Any suggestion? I'm done with my system. What should I do?
Find a desired response.
Very good, very good. Desired response. From where? Where do we get it? Suggestions?
From table 5.
From the table, exactly. Go to the table of this mode. We're talking about the Dutch roll. Go to the table of the Dutch roll, which is the most extensive table. It's a lot. Why it's a lot? Because people really worry about the Dutch roll mode. Pilots are really concerned about the Dutch roll mode, so they seems that they grade everything. It's different. It's unlike the short period, which really didn't care about classes. Here, it's different for every class, different for every flight phase category. They're giving you minimum damping, minimum natural frequency, and minimum time scale. Because remember tau is 1 over zeta omega n, right? Minimum time constant. Minimum zeta omega n or maximum time constant. All right, so we, again, like I said, we use this table in 2 different ways. One, to analyze an existing airplane to determine the level of flying quality. This is the final result to read if I have zeta and omega n. But if I'm designing, I'm going with the level 1 flying qualities to determine my allowable zeta and omega n. So let's do that. So first of all, we said the desired response here. I have, it's a trainer airplane, so it's class 1. And landing, so it's cat C. So I go to the table by level 1 flying qualities. Let's go here. We said class 1 and cat C. Here is class 1 cat C. There is a, where here, yeah. This one, right? Oopsies. Why is this? Okay, done. Class 1 and cat C. So the minimum zeta, we got 3 things from the table. The minimum zeta minimum is 0.08. And the multiplication zeta omega n multiplying together minimum is 0.15. Omega n minimum is 1. So these are 3 limitations, and I need to get 2 of them. So let's decide about what are the minimum things ever. What are the minimum things ever? If you choose, this is the minimum and this is the minimum, like zeta and omega. What's the multiplication of them? Multiplication of 0.08 and 1 is 0.08. This is actually less than this. So you can't consider the minimum zeta as 0.08 and the minimum omega n as 1, because this does not satisfy that. So do whatever combinations to satisfy the 3. This is the usual combination we do, okay? Because this obviously, if you divide the zeta omega n by omega n to get zeta, you get 0.15, which is larger than the min. So the red things here are the minimum requirements coming from the table, the minimum allowable things. And usually, as designers, we give ourselves some margin of safety. Actually, the problem is asking you to take about 25% higher than the minimum, so like a margin of safety. So based on that, like 25% more extra. So you multiply these values by 1.25. I get the actual zeta that I'm gonna design, the desired zeta, or the desired zeta omega n. the desired omega n is simply 1.25, right? Multiplying 1 by 1.25. And the desired z omega n is 0.90. And these are the two requirements that I'm going to use for design, which means that my s squared plus 2 times zeta omega n is 0.38 plus omega n squared. This is 1.56. This is the desired characteristic equation. I'm done with the second step. Any question about that?
Is it equally acceptable to pick the zeta min and zeta omega n min, and then you'd get a higher value for omega n?
That's fine. That's fine.
Okay.
This is the typical approach we do, but it's the other one is okay. It's perfectly fine.
Okay.
Okay. Third step. Any suggestion? How do I proceed further? So I have my system and I have the desired response. Then,
Write it as like find your closed loop matrix.
Very good, very good. Your control design itself, right? Or the control technique, the control law, which here we do state feedback, and the state feedback really makes your closed loop as A minus BK. So let's do that. I'm gonna copy my A matrix. So my A closed loop is equal to, here is my A matrix, minus BK. I'm gonna go and copy my B. Here is my B. And folks, if you have any question, please stop me. This is super important for the final. And also, I mean, it's a nice thing, I mean, to be able to design autopilots to achieve, desired flying characteristics. It's an interesting thing. Okay, so this is my B, and I'm going to multiply it with the K matrix, which is rho, just K1 and K2. Please multiply this carefully. So this is 0 times K1 is 0, 0 again, negative 0.6 K1, negative 0.6 K2. So the BK is 2 by 2 matrix as usual. And now I'm gonna simply subtract these two matrices. So I get the A closed loop as negative 0.05, negative 0, 0.3 plus 0.6 K1. Here is my blue separator. Then negative 0.98 minus 0, negative 15 plus, right, 0.6 K2. This is my A closed loop. I got my A closed loop, and here is the desired response, the desired characteristic equation. So all what I need is to get the characteristic equation from here for the closed loop and compare. So lambda I minus A closed loop is equal to, and I'm gonna copy this. Oopsies, what did I do? Okay, fine. Actually, I'm gonna erase this and replace with determinant. And this was 0.98, and this is my separator. And what do I need to do? I need to do minus A. So I'm gonna adjust all the signs with minus. So this is plus, 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 minus, and this is minuses, right? Now I need to do lambdas over the diagonal. So this is lambda squared plus 0.2 minus 0.6 K2. This is all times lambda plus the free term, which is 0.05, 0.15 minus 0.6 K2 minus, so this is plus 0.3 plus 0.6 K1. This thing is how much? Actually, this is, where can I find it? This is 0.3015 and 03K2. So we simply compare, right, with the desired characteristic equation. We simply compare. So this black term, the free term, is equal to the free term here. And this red term is equal to the 0.38. Actually, this red thing, because it's only function of K2, I can immediately get K2 is negative 0.3. And then substitute in the other equation to get K1 is around 20 or 2.125. And we're done with the gains. But never stop here, because these are really meaningless. For yourself, go and sketch an implementation diagram. I'm not going to do it again. It's very similar to this one. But in the homework and in the final, you're required to write down the control law and explain the physics that changed in the airplane characteristics due to this feedback. So what is my control law? Can anybody say? What is the control law here? What's your input? What's my input?
Delta rudder.
Delta rudder is negative K1 X1, negative K2 X2. So let's substitute. Delta rudder is negative. My K1 is 2.125. Times my first state. What is my first state here?
Beta.
So beta and minus again. So this is plus. The second state was on. This is my control law. Please measure beta every time. And the yaw rate using another gyro every time. Just substitute in this equation to get the right amount of rudder deflection that should be applied every time, continuously during flight. Okay. Let's now try to illustrate from physics. When you apply delta rudder to your airplane, you get what? Applying rudder does what to your airplane?
You get side slip.
Get side force, that's fine, but more over and more importantly, what? Say it again? Yeah, moment. Very good. Yeah, rudder, we just actually, in the very first place, we placed the rudder, or we had a rudder for the airplane to generate a yaw moment, to control the yaw. So in the change in the N is simply N delta rudder times delta rudder, right? So this is, let's get N delta rudder here, please. The issue in this example, really, when they give you the system like this, it's actually harder than when they give you numbers for the stability derivatives, NR, N beta, N delta rudder, because now you need to read them off. Can you tell me what is N delta rudder from this system? Because I need it now. So you have
0.3.
N delta rudder, not NR. Yeah. So N delta rudder is the coefficient that is multiplying delta rudder. Let us read this, folks. What is this equation, the first line? It's for beta. And what's beta? It's actually V over U naught. So I can multiply everything here by U naught and get an equation for V, right? It was for beta dot, now it's for V dot. What's V dot? It's the acceleration sideways. So this first equation of motion is the acceleration sideways equal all the forces sideways divided by the mass. And the same for the second, the third. What's the third equation? This is R, so it's the yaw rate. R dot is the yaw acceleration. So everything here is yaw moment divided by moment of inertia. So this is N due to beta multiplying by beta. This is N due to P multiplying by P. This is N due to R multiplying by R. And the last thing, which is 0.6, this is the N delta rudder multiplying delta rudder. So indeed, my N delta rudder is negative 0.6, okay? So this is, let's do the blue. Fine, so this is n delta rudder multiplying by delta rudder. I'm gonna substitute by delta rudder from here. So it's negative k1, and this is beta negative k2 times r. So my change in the n is negative k1 n delta rudder times beta negative k2 n delta rudder times r. And look at this, changing in the yaw moment is something times beta. What must be this?
Yaw stiffness.
Very good. This is yaw stiffness, which we call n beta, right? And what about this thing? This is what?
Yaw damping.
Yaw damping, which is nr, right? So this is my additional n beta stiffness, and this is my additional nr damping. Let's compute this. Let's just multiply K1. K1 here is 2 point something times n delta rudder, which is negative 0.6. So the change here is how much? Let's see. This is around 1.275. And let's do this multiplication. This is around negative 0.18. And let's compare versus the old values for n beta and nr. Can you give me n beta from here? What is n beta, either from this system or that system? What's n beta, guys? Anyone can give n beta?
0.3.
0.3, yes. Simply the first equation is for the y equation, right? The side force. The second is for the roll. It's the everything in the right hand side is L something. The third is for yaw, N something. So this is really N beta, this is NP, this is NR. Or from here, this is N beta and this is NR, right? So N beta is 0.3, NR is negative 0.15. So this is 0.3 and this is negative 0.15. So look at that. How much additional stiffness you're doing? It's 4 times extra. So again, it's as if I'm multiplying my yaw stiffness by 5 times, because the total will be the addition of the two, which I could have done by doing what in the geometry of the airplane?
Increasing the area of the vertical tail.
Exactly, multiplying the area of the vertical tail 5 times. Again, these are some of the requests that you will get fired if you ask your chief engineer to do. The same here, my yaw damping, I added this much. It was negative 0.15. Now I added in addition, so the total will be the addition of the two. So it's as if I'm adding 100% yaw damping. And these are just by feedback. These are virtual stiffness and virtual damping through feedback. These are the actual values due to the geometry of the airplane, the natural response without the interference of the pilot or autopilot. Any question about that? We're done for the course.